Good day, everyone. My name is Rodney Herring. I'm at the University of Victoria, British Columbia, Canada. I'm going to be speaking today at the 6th International Conference on Materials Science and Nanotechnology. The title of my talk is Imaging the Core of Dislocation and its Annihilation at a Crystal Surface. Dislocations have a great influence on materials property, such as their mechanical, electrical, photonic, sensory, and magnetic properties. Dislocations are the reason why Archie Howie actually entered into the field of electron microscopy to study these defects, and they've been known for quite a while now, for around 80 years or so. This is an image that many of you have seen of an edge dislocation, where we can have an extra plane of atoms in an otherwise perfect crystal. The extra plane terminates in the crystal, and the atomic planes we can see bending around the core of the dislocation. One of the interesting features of the dislocation is that if we do a Berger circuit around the dislocation, we get a 2 pi phase shift over a 360-degree rotation. And whenever we have this situation at the center, there's a physical singularity, and the dislocation, the singularity at the core of the dislocation, may be the smallest known physical singularity. Dislocations have a very complex strain field around themselves, and this is because of the atomic planes. These haven't been able to be studied in detail because we actually haven't been able to measure the strain field around these. We see that the dislocations in structural materials, if they can, at the core of the dislocation, there can be an impurity such as carbon and iron, which forms steel, and it produces Cottrell locking. In electronic materials like silicon, you can have a dangling electron, so the dislocation forms a charge at the core, and is essentially a wire, which when it drifts into the active region of a device can drain the charge and the device fails. In photonic materials such as gallium arsenide, you can have various types of dislocations. They can be terminated by gallium or arsenic. With gallium, there'll be an extra positive charge. With arsenic, there'll be electron, and these will annihilate any kind of charges within the material to stop the generation of photons. At grain boundaries, the misfit between the two adjoining grains is accommodated by dislocations. You can see those nicely here, and they form a two-dimensional network, and they are essentially where corrosion occurs inside materials. So to image dislocations, the core hasn't been visible by standard methods such as Bragg diffraction and lattice imaging, which have the atomic resolution. They're also studied by electron beam induced current, but this is a very low resolution method. So what I'm going to be talking about today is a method to image the dislocations in their entirety, and we're going to follow a dislocation through a crystal and see it annihilate at the free surface of the crystal. The method that we use is, this just shows why dislocations aren't able to be imaged by diffraction contrast, because the diffraction occurs off to the side of the dislocation core. And so we have a contrast off to the side of the core. And you can see that here. Here's the diffraction contrast of dislocations, and where that contrast lies is not actually the core of the dislocation. In lattice imaging, It's a two-dimensional image of a three-dimensional structure, so we can't see things like kinks, intersection points, or any kind of strain relaxation at surfaces. Diffracted beam interferometry involves having a direct beam impinge upon a crystal and the crystal will produce diffraction. What we do initially is align the microscope at the in-focus condition of the specimen. And once we get aligned, we don't touch the objective lens current at all. We shape the beam using the condenser lens and apertures. It can be produce a probe on the specimen, or you can have a planar beam. And then we use the eccentric tilt to adjust the diffraction where it occurs within the specimen, and we can produce a change in focus, which then allows the diffracted beams to separate sufficiently so that they don't interfere with a biprism used to deflect the two beams to an observation plane, such as the diffraction plane. We use the intermediate lenses to image the specimen either at the in-focus diffraction through the right through the Fresnel imaging mode and almost to the specimen in focus. We can't go as far as the specimen in focus, but the intermediate lens allows us to determine which observation plane we actually want to see. We also use the projector lenses to magnify our image so that the fringes that are produced by the interference of the two beams are easily seen by our camera. On to the top right here is a good example of an interferogram. When we Fourier transform this, we can get the phase, and we see in this particular interferogram, in the phase image, we see a dislocation network. This also shows an example of an interferogram here. It has very high contrast fringes. It's the two 111 beams interfering of an aluminum material. And when we can reconstruct that, we see that we have a nice a dislocation network in here. This dislocation here goes from negative phase to positive phase, and then the one over here goes from positive to negatives, so that forms a very nice network in here. And so we get to measure what the phase, and the phase represents the strain around the dislocation. The dislocation I'm going to be talking about in this presentation initially looks like this, where we just see two little blobs in the bright field image. When we set it up for exact Bragg, having the plus or minus 220 diffraction vector, we interfere those, and you can see the fringes from the interferogram. When we Fourier transform this to get the phase, we can see that there's the dislocation passing through the crystal here. There's two termination points. This one here is the top of the crystal. This one here is at the bottom of the crystal. If we magnify this region here, we see that the dislocation, as it approaches the surface, that it goes unstable and it forms something that appears like a volume defect. The bottom of the crystal is imaged because the diffracted beams actually separate out their virtual sources, and now you can do differential phase contrast imaging. This isn't possible at the surface, so we can't see the surface, but we can see nicely the bottom surface, and we can vary the separation by the thickness of the crystal that's being imaged. So on the right here is an example, and we can see here there's a amorphous carbon spot on the bottom surface of the crystal and a dislocation network passing down here. Getting back to our specimen, we see this thing that appears like a volume defect. If we phase amplify it by 2 pi divided by 3, we see that the dislocation here where it's going unstable actually forms a couple other dislocations, and there's a triple point right here, which is also a singularity. So one of the questions I ask, what is the smallest singularity, physical singularity? Is it the core of the dislocation, or is it this triple point where the dislocation is splitting into 2 other dislocations? And so in this case, what we're doing is imaging the dislocation from within the crystal to the surface, whereas normally we see these dislocations on the surface forming etch pits, but we can't see any detail in these. So the model that I'm going to present is a dislocation that's splitting into 2 dislocations to form a triple point. And then those 3 dislocations can actually further split into partial dislocations, forming 3 stacking faults, which form 3 surfaces to create a 3-dimensional pit. So here I start with a 1-1-1 plane within a face-centered cubic. My specimen is gold, and the deformation planes are in the 1-1-0 directions. And you can see here we can have a possibility of 6 1-1-1 deformation directions on the 1-1-1 planes. So you can have a dislocation having D, the interatomic spacing of the 1-1-1 plane, divided by 3. This is the Burger's vector direction, the O1 bar 1, lying on the 1-1-1 plane. It can split into a D divided by 3 bar 1-0-1, as well as a D divided by 3 1 bar 1-0. So if we add these 2 vectors here, they come out to the same vector here. So there's nothing, everything's consistent. These dislocations can move off one plane onto another by cross-slip. So the O1 bar 1 dislocation can cross-slip over to the bar 1-1-1 plane. The bar 1-0-1 can cross-slip over to the 1 bar 1-1 plane, and the 1 bar 1-0 can cross-slip over to the 1-1 bar 1 plane. And when these dislocations can further split and form partial dislocations, and when they form stacking faults. And here we have a stacking fault, which is a surface, and we can see a partial dislocation here and a partial dislocation here at either side or end of the stacking fault. And this creates a surface. So each one of these 3 dislocations can form partial dislocations. So the D divided by 3 O1 bar 1 can form a or 2 partial dislocations having D divided by 6 bar 2-1-1, which will form 1 surface. And then likewise, the other 2 dislocations can form the 1-6-1-2-1 1 bar 2-1 type of dislocation. So we can generate 3 dislocations from these 3 stacking faults. And if we were to look at this in a unit cell, we can see the 3 stacking fault surfaces here. So the red one is a plus or minus D divided by 6, 1-1-2, 1-1 bar 1. So this is the 1-1 bar 1 plane. The green one here, there's another surface in here. It's a D divided by 6, bar 2-1-1. It's on a bar 1-1-1 plane. And then we have the third one here is D divided by 6, 1 bar 1 bar 2-1 on the 1 bar 1-1 plane, and that's here. And so we have these 3 surfaces which are intersecting at this point in here. And what's interesting is that each one of these each one of these surfaces share 1 partial dislocation. And this reduces the energy and allows for relaxation of these surfaces. And so this relaxation can actually eject at the atom that's within at the corner here. And when this ejects onto the surface, then we can actually form the three-dimensional pit by forming a three-dimensional volume. The stress or formation energy is thus required to nucleate the pit is 1/2 the energy of the dislocation. So the formation energy sigma is approximately 2 times the elastic modulus times the strain energy. And the strain energy for the relaxation is 1/2 times the Berger's vector. And as a result, it's just the elastic modulus times 1/3 times the interatomic spacing, the 1-1-1 spacing. And when we calculate this, the elastic modulus is 76 gigapascals, and the strain is 0.078, and it gives a formation energy of 5.9 nanometers. One interesting thing to apply this in the future would be to look at how cracks are formed. An example here is a crack forming in steel, where you have the movement of glide dislocations from 2 planes intersecting with each other to form sessile dislocations. And when they build up, they actually form a 3-dimensional crack. So this has never been seen before. So I think this method will allow this mechanism to be studied. So in summary, the dislocations in their entirety can now be phased imaged. The strain profile of the core can be measured. Annihilation of a dislocation at a free surface producing a pit could be imaged. The proposed formation mechanism of the pit produced a formation energy of around 5.9 nanonewtons in gold. And from this work, or method of imaging dislocation, many material properties affected by dislocations can now be studied in greater detail. And I leave you with a question: which physical singularity is smaller, the one at the dislocation core or the 3-dimensional triple point of the pit? I want to acknowledge Arthur Blackburn and Elaine Humphrey for maintaining the Victoria's Advanced Microscopy Facility in a state-of-the-art condition. And I also want to thank my funding sources of the Canadian Foundation for Innovation, the British Columbia Knowledge Development Fund, and the Natural Science and Engineering Research Council Discovery Grants. Greatly appreciated. Thank you very much. Please, if you have any questions, let me know.